Hello, everyone, and welcome to day two, or the second broadcast of our Monsoon Awareness Week. Yesterday, we had a great discussion with several weather offices around the area, around the Southwest, and we talked about flash flooding. But tonight's theme is lightning, and it is certainly an underrated killer. We've had problems with the problem with lightning is that it strikes one person here, one person there, all across the country. Maybe it makes the local news, but you don't hear about lightning strikes very often. So it is one of the higher rated killers, and we'll talk about all of those things. We'll talk about a little bit about safety. We'll talk about what lightning is, how it forms, all of that tonight on our live broadcast. So I'm so happy that you were able to join us, and I want to go down the line here real quick and introduce everyone. First of all, from the Sioux from the Phoenix office is Paul Enriquez. Paul, how are you, sir?
Doing just fine. How are you doing?
Doing well. And then
Fantastic.
from Vaisala is Ron Holly. He's sitting in at the Tucson office. So, Ron, how are you doing this evening?
Doing well, thank you. Good to be here.
Very good. Ron is our subject matter expert. Vaisala runs the national, what's the words I'm looking for? The National Lightning Detection Network, is that it?
NL, the National Lightning Detection Network.
Very good. And finally, also joining us, just getting in as he's tooling around, is Alex Tardy, the WCM over in San Diego. How are you, Alex, today?
Hi, Tim and everyone else. Good to be on and to talk about lightning.
Very good. Well, let's just jump right in. And Ron, can you basically tell us how does lightning form and maybe describe what lightning is?
Well, lightning is an important part of the whole electrical process of the atmosphere. One of the famous researchers told me a few years ago that if we didn't have lightning to equalize the upper and lower part of the atmosphere, every time we reached out for a doorknob, we'd have a spark about a yard long, which I don't think that'd be a whole lot of fun. So it's a way to equalize and balance out where the charges are. So it connects the upper with the lower atmosphere. The essential ingredients for lightning are to have an updraft, vertical motion going up through a deep part of the atmosphere up to the level where there's a mixture of small hail, ice particles, supercooled raindrops, and ice crystals. And when that updraft gets into a level that's colder than freezing, always colder than freezing, then you can have lightning.
Very good. So, the way I picture a thunderstorm is like a big battery, and you got positive on the top and negative on the bottom. Is that a real kind of rough way to think of a thunderstorm?
Yeah, it is, and that's part of the process of equalizing out all the charges through the atmosphere so that we don't have those big sparks.
Exactly. Now, as the thunderstorm develops, it's got we got a positive charge on the top of it and a negative charge on the bottom of it. Hey, Paul, if you could you maybe call up a schematic of a thunderstorm with a plus and minus on it and throw it up on your screen? And so as that thunderstorm moves across, it starts to induce, or it makes a positive charge on the Earth. Is that right? Is that how it works, Ron?
Right. It induces it just like you have a little magnet on a table and you have some metal parts a few inches apart. It sort of gradually pulls toward the magnet.
And then eventually that difference, because it keeps building up, the charge keeps building up in the cloud, and the difference between the cloud and the ground continues to build up, that you start to get the step leaders come out of the cloud, and they work their way. Let me, I'm going to throw Paul's screen up here so everyone can see what we're talking about. But you can see those little step leaders start to reach out from the bottom of the cloud. We can't see them, but as they reach down, they're looking for the best way to get to the ground, and eventually one of them touches the ground, and you get that brilliant return stroke that runs up the channel, taking that charge. And does it lower negative charge usually, or does it bring up positive charge? How does that work, Ron?
Well, about 90 to 95% of cloud-to-ground lightning flashes lower negative charge to ground, so that 5 to 10% of positives is a relatively scarce event.
Right. Now, but having said that, with the majority of them being negative strikes, but if I remember right, the positive strikes are the ones that actually they usually last longer, they're hotter, and they tend to be the ones that can start forest fires or any kind of fires because the current stays going for so much longer.
Yes, it's something called the long continuing current, LCC. Long continuing current is more common with positive flashes. I think the last number I heard was around 50%. The only thing is that there's also long continuing current in some negative cloud-to-ground flashes, and so there are quite a few long continuing current events with negative flashes also. So we can't. It isn't as simple as you'd like it to be, but that's
exactly.
that's
It never is when it comes to the weather.
Right.
Hey, I forgot to mention, if anybody who's watching has a question, feel free to tweet us a question at hashtag Monsoon 2016. Hey, Paul, can you run down real quickly some lightning safety tips for people? Let's say for people who are outside doing outdoor activities.
Go inside. That would probably be the first one.
Check.
Other than that, you don't want to be under tall objects, obviously. You don't want to go under trees. You don't want to be around light poles and things like that. You don't want to make yourself the tallest thing out there, swinging golf clubs, things like that, baseball bats, sitting high up in bleachers, We see more and more pictures, it seems like, where you have stadiums full of fans and they're sitting in the nosebleed section and you see the lightning strike off in the distance, and guess what, those $20 tickets in section 300 are making you a prime target now for that lightning. So big thing is to get indoors, and if you're not indoor, if you don't have that option, and maybe Alex could help out with that. I know that there used to be the crouch and make yourself into a ball, but was that kind of scuttled a bit lately now?
It's completely gone.
All right. So what should I do instead, Ron?
Well,
I'm
the underlying
here.
thing, there's two reliably safe places. One is inside of a large, substantial building, like a workplace or a home or a school, and the other one is a fully enclosed metal top vehicle. Other than that, you have no certain safety, and a lot of the safety advice that's out there has been around for a long time is based on a very flawed idea, and that is that lightning comes down and hits people in the head. We have done quite a bit of looking. I've looked at thousands of cases, and it almost never happens, maybe 3 to 5% of the time. So the crouching and all those things are the responding to something that isn't really the threat. The most common threat is ground current, where it hits fairly nearby, and then the tendrils come across the ground to people on the ground. And you can't predict where they're going to be. You can't predict how far away it's going to be, and so on. So really the safe place, the reliable safe place, is a large building or a fully enclosed metal top vehicle.
It used to be like Paul was kind of hinting at. It used to be that people thought, I'll lay down. And that's a bad thing to do, just because Ron said if you put more of your surface body on the ground, you're more likely to get that current if it struck nearby, if it struck a tree where the roots are coming around, or even it just struck the ground. If you're laying fully on your body down on the ground, you're more likely to take that charge into your body. So then later on, they said, well, we'll just crouch down and make a little ball. And like Ron is saying, you're still got your feet on the ground. It's still just not a good idea. The best place to go in a thunderstorm is inside a sturdy building or a metal car, fully covered car. For those of you that drive convertibles, well, I'm sorry, it's not going to work in a lightning storm because you've got that cloth on top. It's got to be a metal car, and I think the word for it is a Faraday cage that keeps all the electricity on the outside of the metal. I tell the kids when we go to schools that if you pour water on the top of a car, it flows down the sides and around and down to the ground. Electricity behaves very similarly to that fluid. It stays on the outside of the metal, so as long as you're inside the car and the lightning strikes it, it flows down the sides of the car, down the axles, and actually I've heard stories that it shoots holes through the tires and things like that. So a lot of people believe that cars are safe because of the rubber in the tires, but a lot of times they actually put a big steel belt in there to make them stronger, so there's a big metal belt in your tires. It's not the rubber of the tires that keeps you safe in a car, but actually it is the the metal skin of the car, the electricity likes to stay on the outside of that. Does that sound about right, Alex?
Yeah, that sounds right. Can you guys hear me okay?
Yeah, go ahead.
Yeah, the thing about lightning that's so fascinating when it comes to safety and the science, every time I listen to Ron, I learn something new, so hopefully everyone's listening in. But it's so unpredictable. And, I used to go to bed as a kid watching lightning, watch the lightning. They called it heat lightning, but all it was a distant thunderstorm lighting up the night sky, and you could see the rim of the cloud. But when you're outside, not everyone's a meteorologist, and not everyone's studying the cloud formation and the updraft that you guys mentioned. And it's often too late, and lightning can just suddenly strike, and it seems like it's out of nowhere, but the warning signs, if you really pay attention to what's going on around you, are really there. It's not like heat or heavy rain where it's obvious. It's something that's more subtle, but you need to really be paying attention. I was out at an event last summer in the Northeast. No one was paying attention, and within about 30 minutes, it was a farmer's market. People were scrambling, and they weren't just scrambling because it was about to pour. It was because there was a lightning strike nearby, and it caught them all off guard.
Hmm.
But for you and us, as meteorologists, we're seeing all that, but it's just not that obvious to most people like heat or heavy rain would be, and it's difficult for people to take precautions. So whenever you hear thunder, absolutely.
Yeah, I think he was going to say there, when thunder roars, go indoors. That's the saying for the day for Monsoon Awareness Week. Hey, Ron, he talked real briefly. A lot of people use the term heat lightning. And I think a lot of people actually think that lightning is generated by the heat. Can you kind of expose that myth that there is no such thing as heat lightning? And what are the people actually seeing when they see lightning on a warm summer night way off in the distance?
Well, I grew up in the Midwest, and that was a common phrase. It's also common in a lot of other places. You can see lightning, especially here in the southwestern states, up to 50 or 75 miles away on the horizon. You know how far you can see it over a mountain range, quite a long ways away. The thunder can only be heard up to about 10 miles, really in a quiet situation, no wind blowing, no trees, no traffic, maybe 15 miles. So that long distance, an area beyond 10 or 15 miles is where you can see lightning, but you don't hear thunder. And in the Midwest, lightning and thunderstorms tend to occur when it's warm, and quite a few of them are at night. And so this process comes up with the idea of heat lightning, but it's absolutely normal lightning where you can see the flashes, but you can't hear the thunder.
And that's very true. Like Ron, I grew up in Oklahoma, and I was always told that's heat lightning when you would see lightning way off in the distance. And it wasn't until I went to school that I learned that that's just a regular thunderstorm that's real far away that you can't hear the thunder with. So, hey Ron, can you describe an actual lightning bolt? Because when you look at it, it looks huge. It's this big. It looks like it's giant white finger that sticks down. And if I understand things right, it's actually not that wide. And then, how hot can lightning be actually?
Well, first thing is the lightning channel itself is only about an inch in diameter, maybe less. And so when you see it with your eye, it tends to saturate your eye and look bright. And in photographs, it tends to look much bigger than it actually is. If you photograph it very close up, with a lot of lightning scientists are doing that now with high-speed, high-quality cameras, see it's a very thin, small channel. The temperature, though, is 30 to 50,000 degrees, I think it's Celsius, and so it's very, very hot. The only fortunate thing about that is that the typical lightning event only lasts a portion of a tenth of a second, although there may be some following return strokes. So it's a very fast but very intense event.
So the channel itself is actually pretty small, like you were saying, and it's the heat, like you said, 30 to 50,000 degrees Celsius. It's the heat that actually makes the thunder sound that we hear, right?
Yes, it's actually demolishing the molecules. It's ripping apart the atoms.
Wow.
Yeah.
I think of thunder as if you're on a hike and you put your foot down and you hear a rattle, you jump back because you know there's a rattlesnake right there. And I think of thunder is the same way. If you hear thunder, lightning is nearby, and you know what? It could get you. So in many ways, I think of lightning or thunder as the rattle of lightning, and it's just warning you, hey, I'm nearby, and I could get you. But hey, Paul, tell me truth. Tell me if I'm right. Sometimes you don't get that first clap of thunder to warn you that it's about to, the lightning's in the area, right?
Yeah, sure. I mean, it's going to always be possible that first lightning strike that we get is going to be a cloud to ground strike. I don't know the exact percentage. Maybe Ron knows, but I think it's roughly 90% of lightning strikes are intra-cloud lightning, cloud-to-cloud strikes, whereas about 1 in 10 actually hits the ground. So you're not always going to get that heads up that something's coming your way.
Yeah, part of that is that the cloud lightning is, I think it's about 4 or 5 times as many. I don't know what that percentage is, but when you have lightning in the clouds near or overhead, that's just as dangerous as the cloud to ground lightning is in terms of safety. You need to heed that as a sure sign because you don't know whether the next one will be in cloud or cloud to ground. There's really no difference in terms of the threat.
One of the threats that people don't really think about, because we always think about lightning as being like with all the rain and the activity right at the core of the thunderstorm, but you can't get lightning out of the anvil of the thunderstorm. Is that right, Ron?
Yes. We have a problem here in the southwestern states, and this is the area where this issue arises, is that a fair amount of lightning occurs without it actually raining at the ground where you are or where the lightning strikes. So easily 10 to 30% of all lightning occurs without raindrops falling where you are. So that makes the mantra that we have is pay more attention to the lightning than to the rain when you're in a situation where you need to make a decision, because the lightning is a much more important issue.
Now, Paul, help me. I was doing a little research for today's broadcast, and I came across a saying that I found kind of interesting, and maybe you can help explain it. That just like Ron said, a lot of lightning strikes without the rain actually reaching the ground, and in the Southwest and in the West in general, many forest fires are started by what we call dry lightning. But can fires lead to the development of lightning? So you get lightning starting fires, but can fires themselves lead to the formation of thunderstorms and lightning in that way?
Yeah, additional thunderstorms, definitely. So when we have large fires develop, you're getting a lot of combustion of material. It's generating a lot of heat, and that's rising air. You mix it in with some of the either moisture that's already in the atmosphere or moisture that's being released from the fire itself, burning up all the biomass, and you can get pyrocumulus clouds. They're clouds that are just developed because of all that hot air moving up, and if they become big enough, if there's enough heat moving upward or the air is already a little bit unstable, that can take off and you can get additional thunderstorm development from there. And additional lightning. So I mean, it can happen. Doesn't happen with a lot of frequency, I would say, but it's very possible. It's not like it's something that we never see.
I like that word, pyrocumulus.
Some of the most fascinating photos I've seen. Some of the most fascinating photos I've seen is over a volcano where you have thunderstorms that form.
And again, if I understand, Ron, it's just a matter of that friction. In the case of thunderstorms over a pyrocumulus over fire, it's the friction of that debris that's being drawn up into the thunderstorm. Over volcano, you've got the volcanic ash kind of rubbing. It's the same kind of concept. If you walk across a carpet floor on a dry winter day and reach out for that doorknob, you get that shock. Is that right?
Well, it's sort of like the thunderstorm with water particles. In the volcano situation, you have an updraft. It's blasting stuff upwards. It's blasting different size particles upward, and some of them are large, some of them are small, and as they go through the atmosphere, they take on different charges, and the heavier ones fall right back down, and then they're next to lighter ones with different charges. That's essentially what happens in a cloud with hail and raindrops and ice crystals. So you have a separation of charge based on size. So the volcano actually is doing sort of what a thunderstorm is doing, except it's doing with rocks and dust and all sorts of other things.
Amazing. Now back to lightning safety. I think I read the statistic that on average 49 people each year die from a lightning strike. Hundreds more are injured. The vast majority, or I shouldn't say the vast majority, the majority of those struck by lightning are men. Ron, can you talk about why men seem to be favored when it comes to lightning?
Well, that's an interesting topic. I've done a lot of work on the demographics of lightning deaths and injuries going back about 200 years now. Not my lifetime, but 200 years worth of data I found way back to the early 1800s in some European countries. For the most part, it has been 80 to 90% male, and the general prevailing attitude is that it's a male attitude issue. It's not occupation, attitude. And that is that males tend to take risks. They tend to go stay out longer. They tend to go into situations where there's thunderstorms with a certain amount of attitude that it's not going to affect me. I'm doing a study right now, actually presented recently, doing a lot of international work, and I've studied 1,000 or so deaths in India and Bangladesh in the last 10 years. And in that situation, it's almost 50-50, male and female, because many or most of them are involved in labor-intensive agriculture in rice paddy fields. So that actually tends to be more of a woman's work, where it's very long labor and large numbers of people are out doing this. And so in the developed world, like U.S. and Europe and Japan and Australia, it is 80 to 90% male, but in labor-intensive agricultural countries of Africa and Asia, it is about 50-50.
Hey, Paul, can you talk about what's up on your screen right now?
Yeah. I thought I'd show a little bit some analysis, some different lightning data I was playing with a while ago. This is from the NLDN, just what Ron was talking about. And, you know, we get some pretty significant lightning storms, as we've just been talking about. Here was for one particularly ferocious storm that moved through the Phoenix area back in August of 2008. So this was the lightning strikes across the entire country for that day. And if I look at just what we had on that specific day, so here's a map of Arizona, and this is starting at about 5 p.m. in the evening until 5 a.m. that morning. And so each one of these dots was a cloud ground lightning strike, and the color tells roughly what time that lightning strike occurred. So any of these really dark dots were right at the beginning, so it was around 5 p.m. And as we go towards some of those reds and oranges, that's getting to about about 10 p.m. and then some of these orange dots here are later in the morning. So you can see, just using the lightning data, we can see right where the storms went. They originated up to the northeast of Phoenix and to the northeast of Tucson, and as these waves propagated, as they moved to the southwest and they got into the lower elevations, you can see they just really took off and just got a ton of lightning right over the city. I just have a little statistic here that within 50 miles of downtown Phoenix, there were nearly 6,000 lightning strikes during this evening. And then the storms moved off to towards Yuma during the early morning hours. So this is was a big storm that a lot of people remember around here in the Phoenix area.
Is it typical for thunderstorms? Because I assume that off to the northeast that's higher terrain. Thunderstorms form off the higher terrain of that are off to the northeast of Tucson and Phoenix, and then they move down into the lowlands.
Yeah, let me see if I can find. I know even Ron's done some work in the past showing lightning density across the Phoenix area, and here we go. I got what I'm looking for.
And then Ron's got a map up that I'll have him talk about here in just a second. I was actually going to show that map. He beat me to it.
Yeah, I mean, Ron can talk about it too. So I mean, the thunderstorms, they start over the high terrain over central and southeast Arizona, and then they tend to move. Stereotypically, they move to the southwest, and you can see this in a lot of different lightning data. I've plotted up the different lightning for different days, and it's kind of interesting looking at these maps. It kind of shows you how different each day can be. Here's just some random day showing where the lightning was really about 5 p.m., and we get some of it moving down into the lower elevation. Sometimes we get real intense thunderstorm activity. Sometimes we don't get much. Phoenix covers a pretty large area in here, so you can definitely have like this just random day here. It was really what we would call the East Valley got clipped by this storm here. The vast majority of the metro area didn't get anything. Here's a little bit up towards like Sun City. Here's just a bunch of random stuff. Really during the overnight hours, it looked like. And Phoenix is in this really unique area of the country. It's basically Phoenix, and also I believe the Upper Plains during the summertime are the only locations in the country that have a lightning maximum that's during the late evening or like early morning hours. So typically Phoenix is going to see most of its lightning activity between roughly 8 p.m. and 12 a.m. or 2 a.m. or so. And that's because of that convergence of the thunderstorms. The thunderstorms develop around the city up in the mountains during the afternoon hours, and it takes time for them to either move down into the lower elevations or for them to throw the outflow boundaries that eventually smash into each other and cause additional storms to develop. And so we get this delayed response that the thunderstorms are not necessarily driven by the sun here. So it's kind of a unique situation for us to be in.
Exactly what you're talking about. And El Paso has a very similar thing, that thunderstorms form up over the higher terrain, over the Black Range, the Gila, the Sacramento Mountains, and across the mountains of northern Mexico, and then they work their way off those mountains, and they all work down to the lowlands, and many times it's like a donut that is slowly decreasing the donut hole in size. With El Paso is many times the middle of that donut hole, and either they just move into El Paso well after dark, like you said, or they put out those outflow boundaries that help to form those additional thunderstorms once and then they get up and cause other thunderstorms to form, those outflow boundaries, and then that gives us our lightning later in the evening, like you said, 10, 11 o'clock at night. So Ron, what map do you have here? What do you have?
All right. Are you seeing it now?
Yes.
Okay, this is the last 10 years, 2006 to 2015. This is a 2-mile grid of the whole U.S. of cloud-to-ground lightning flashes. There's about 20 million flashes per year. So there's about 200 million flashes in this map over the 48 states. And just looking here in the southwest, you see well, first of all, you can see a lot of lightning over Florida and on the Gulf Coast. There's also a fair amount going north along the plains, but it decreases from east to west due to the lack of availability of the Gulf of Mexico moisture. Just doesn't make it over here as often. Then you see a lot of variability across the area of the monsoon. There's a huge maximum down south. I wrote a paper on that, was published last year. The maximum is much larger than Florida. It's the biggest maximum in North America is down a few hundred kilometers south of Tucson. So here you can see the maximum from the Mogollon Rim and the White Mountains as it comes in from the east in the afternoon and evening. Also the lightning storms that come up from the southeast, from southern Arizona. And I remember years ago when I first was visiting Phoenix, it was called the Pac-Man, that it actually kind of surrounded and ate up Phoenix, so to speak, like in the old days. So you can see the minimum here, this is on the west side of Phoenix, and then it just gradually decreases because the mountain effects have less and less effect going westward. Then over towards San Diego, you see a maximum during the monsoon season with some easterly flow bringing the lightning all the way over to the mountains east of San Diego. So there's a lot of variability in the west. I mean, you just look all over the western states. The topography is a very major issue, with much more variable than it is in other places.
So, Alex, as Ron was kind of showing there, you have kind of a minimum of lightning data, or not lightning data, but a minimum of lightning activity. how do you get the word out to people that they need to take lightning safety seriously when you get a lot less lightning than say places even just a little to the east of you guys in like Phoenix?
Yeah, Tim, it's a particular challenge in our region. What we've been noticing the past couple of years with the really warm temperatures and warm ocean conditions is what we call elevated thunderstorms, and thunderstorms that don't necessarily need mountains or deserts or even hot temperatures to get kicked off of. And these type of storms, these type of lightning events occur in the night and the day, and they can even occur when we have normal cloud cover coming in from the cool marine ocean. So they really can catch people off guard. And these type of events have, caused beaches in the past 2 years to actually close and cause people to pretty much just run for cover. So what we're doing now is spending a lot of time with the lifeguards. They've recognized the threat, and we're working with them to really get the message out and remind people how to be better prepared or recognize changing conditions with lightning, because it is still a rare event. It's only a few times a year, and unless they're used to lightning, like they see out in the desert and mountains, they may be very unfamiliar or unexpected to see lightning activity all the way to the beaches of San Diego. And typically it's July, August, and sometimes September when that does occur, like you guys showed on the map.
Very good. Now, we did get a question in on Twitter, and the question was, and anybody can answer this, is there any, Franny sent this in, is there any equipment a person can buy for lightning detection?
Well, I could answer that. You basically get what you pay for. The National Lightning Detection Network's been around for 32 years, and it's used by customers such as utilities and the Air Force and NASA and so on. And the precision is down to a couple of hundred meters, a couple hundred yards. And so even some of our customers aren't happy with that accuracy. So that lightning detection is a solved problem. It does take quite a bit of funding to run the network, but you can buy the data from all sorts of private vendors and all sorts of venues, many different places. As you go down in cost, you go down in detection quality to the point where you just know that there's lightning around. You can reach a point where you just turn your AM radio on to 5:30 or 5:50 AM and you can hear static, and that's another type of lightning detection. But if you want to know where it is and how far away it is and which way it's moving, that's all been done, and it's all done very well. So it's something. It's nice to look at things like an AM radio type of thing, but I would never use it for human safety. Let's put it that way.
Again, if anybody has any questions, they can tweet us a question. Use the hashtag Monsoon 2016. I know that I've seen it like venues like swimming pools, outdoor swimming pools where a lot of people gather and things like that. They have something that's called a field generator that helps detect lightning. Can are you familiar with those, Ron?
Oh, those are called field mills. They are detecting over a variable range what's going on in the immediate environment that's good for a few miles, but by itself it doesn't tell you where it is, it doesn't tell you direction, it doesn't tell you which way it's moving. And so when it goes above certain threshold, it's directly overhead, and I'm not sure that's much of a warning either. There's a problem in lightning detection is that it can be done very, very well, but it does cost a little bit of money. But not doing it well at all is a question of whether you really are solving the problem. And I have a difficulty with going cheap with something that can affect a human life.
Right. Hey, Paul, are you showing us things here? Should I be putting your screen up?
What am I putting up here? Google searching and whatnot.
It's a Google search right now.
Let's see. I did have one thing. Let's see. I did. You talk about this. There's new research that NASA put out, and they used lightning from the Tropical Rainfall Measurement Mission, TRMM, data about 16 years of lightning lightning data, and they indicated that the lightning hotspot was not in the Congo of the world anymore. They're saying it is in Venezuela.
I have a map up here.
Okay, let me put Ron. Let me put your map up here, and you talk about. Okay, go ahead. Share. Look at your screen.
Okay, this is from the new lightning detection network called GLD 360, Global Lightning Data Set 360. This is 4 years, and let me look at here. This is approximately 4 billion strokes detected by this network, and you can see the maximum, the one over the Congo here, eastern part of the Democratic Republic of Congo. There's also a maximum over through here. I'm actually writing a paper comparing lightning there with the one in Africa. There's also huge maxima in lightning in Southeast Asia, and you can see our monsoon lurking to the south of us in Mexico. So this really gives a good indication. This network has just been upgraded, and now it's detecting this summer about 4 million strokes a day, and it's just really fascinating. We have a real-time display of this. So we do know where lightning is, and this is a continuous network that doesn't have holes or gaps or anything else like radar does. It's absolutely continuous. So it's a fascinating thing as a meteorologist. There's a lot of interesting things to look at here.
You know, as I'm looking at the picture, I'm just going to leave it up on the screen. It strikes me that no pun intended. Sorry, sorry about that. But the pictures, one of the things that strikes me is that how the lightning, real roughly, kind of runs right. The lightning maximum runs right along the equator of the Earth.
Right, right. Yeah, definitely. This place in Africa and also the one in northern Venezuela, we can argue about cloud versus cloud-to-ground detection with the networks in the satellite. These places have lightning essentially 12 months a year. We're actually also doing a study on Kuala Lumpur, which is right here, and they have lightning almost every day. And so to the south of here, there's a winter minimum because the equatorial trough moves north. And north of this maximum, it moves south, and there's a few dry months. But this one place here just doesn't really ever have a break.
Hey Ron, it's really interesting there too, like the north coast of Australia. I didn't think that was so high.
Yeah, that's a very concentrated one. It's almost like the monsoon here. It's just July, August, September, and corollary months in the southern hemisphere.
Wow.
Now, do you have a map that shows? So this is a density for an entire year. Do you have anything that shows like a frequency, number of days per year? So which grids are getting the most days of lightning each year?
That's something we're going to do. I would like to do a month of the year, the maximum month. That's studied. We're just getting this data set up to a size that we can do that. So, yeah, I'm certainly thinking of, for example, over Brazil and so on. It's more of a summer phenomenon. In the winter, it's relatively weak. So, yeah, a lot of fun things to do as a meteorologist. We've done this with the U.S. with the LDN for quite a long time, but now we have a new angle to look at it.
Hey Ron, as I'm looking at the map, is the network, does it just not detect lightning over the ocean, or is there just a lack of lightning over the oceans?
There's a lack of lightning over the oceans. These sensors in this network are unique. They have a range of up to 5,000 kilometers, and they're located all over the world. So we can actually track storms leaving South America all the way across the ocean, going toward Africa, but there just aren't very many. So it is a real minimum there.
Very interesting. That's a great.
So Ron, why is there no lightning over the ocean, or very little?
Well, we go back to the original idea that you need strong updrafts, and strong updrafts are much easier to produce over heated land. And heated land is more common in the tropics. And so a lot of the things you see here are coastal effects, like over and mountain effects over Southeast Asia, and the monsoon over northwest Mexico is both a coastal effect and a mountain effect. So you have the heating, you have boundaries set up along coastlines, you have updrafts produced by mountain barriers, and those are just much more frequent than over the relatively cool and uniform oceans.
Does it have anything to do with the any like particulate matter in the clouds themselves?
That's an area that's just really beginning to emerge, the idea of the aerosols, but you just don't have the updrafts over the ocean. If you fly across the oceans, you generally look out and you don't see huge squall lines or big updrafts like you do over land.
It's really interesting, though. I mean, if you look at it, you can just really get a sense of the, the atmospheric motion that takes place on our planet.
Mm-hmm.
Yeah, since this is a very continuous coverage network, it's a really interesting situation. I could divert a little bit and say I was in Zambia. I don't know if you can see the mouse, but this is a country right here. We had a meeting, first African lightning. Oh, it's this country up here. First African lightning safety meeting ever was held, and it was just south of that maximum over the Congo. And, very interesting. People there have absolutely no idea about any of this. So, a long ways to go.
Very good.
That's really, you bring that up too, and that's a real interesting just part of the outreach, I guess you could say, that the United States government does with other countries in the world is sharing our scientific knowledge too. And I know that we do a lot of that with the developing world.
Yes, yeah, it's actually I'm spending a lot of my time in that, and I'll just put a plug in that there was an event, a 3-day event during May, around the middle to late part of the month. There were 81 people killed by lightning in Bangladesh in a 2 or 3 day period, which some of you may have seen about that. And so there's suddenly been a lot of attention paid to that. There's actually a maximum in the lightning over that area too, but just very large numbers of people outside working during the day, so it's a problem.
Hey, Paul, I got another question on Twitter, and it's actually for the Phoenix area. When was the most active lightning in Arizona? What time of year is the most active for lightning?
For the year, I mean, it's definitely going to be the summertime. If there's, I mean, we are usually, of course, monsoon starts tomorrow, and it's going to go through September. Really, July, we don't really start getting a lot of activity in the Phoenix area until after the 4th, mid-July or so. And it's going to keep up probably mid-July to like early September. That kind of 8-week period in there is really where we're at. If I don't have any of my data or stats in front of me, but I was playing around with some of that LDN data, trying to figure out what is our most prolific lightning event we've had in the Phoenix area. And if I dug and did some more research, I could definitely come up with it, because that seems to be something that people are always interested in. It's like, oh, how many lightning strikes were there? And a challenge that we had, I would say up until the last few years, is that not that the LDN data is bad, but it's only showing us the cloud-to-ground strikes. And like we mentioned, a lot of them most of the lightning strikes are in the cloud still. And so we are getting access now to that data that shows cloud to cloud, and that's kind of just a blossoming area of research as well, is that we're seeing a lot of interesting activity with lightning jumps and things like that. So when I'm man on the street, I observe lightning. I necessarily don't care how much there was, if it was in the cloud or on the ground, but trying to get counts on that just for general curiosity is something we try to do. Reporters are usually asking us those questions. I can't say right now what our most prolific day was.
I have to say two things. One is that the NLDN does have cloud lightning. It has for a long time, but it tripled the capability back in 2013. I don't know if you're getting the data. The data have been around for lots of people. So one of my campaigns is it needs to get into the offices. The other thing is that I do have some statistics here. I remember Arizona as a whole has 76% of its lightning in the year during July and August. 76% in July and August. And for the other 47 states, it's 45%. So it's a very concentrated lightning season here in Arizona. During that period, we actually are close to the same amount of lightning that Florida has. It's just that it starts around the 1st of July and ends early September.
And I know, Ron, that that would probably be the same. That higher statistic would hold for like Southern California and
Right.
southern Nevada and New Mexico, even far west Texas.
Right.
Very good. Well, let's talk real quickly. I wish Alex didn't have to drop off, but maybe we can try to talk this through. Large venues. One of the latest things with large venues is lightning safety with these big baseball games, NASCAR, soccer games, where there's lots of people in these venues, and a thunderstorm comes rolling up on the venue. I don't know, Paul or Ron, if you want to comment. What is the Weather Service doing, or what is precautions that the large venue owners or directors can do when they start to see thunderstorms form, and what actions should they be thinking of and taking?
Yeah, I know that we weather offices are conducting, working with, the entities at football stadiums and baseball stadiums, getting them storm ready and things like that to just have that relationship to start with, and then if they need specific lightning data, there's lots of vendors out there that can provide them with that information outside of us specifically.
I have a couple of comments on that. In fact, I have a lot of comments on that. This morning or yesterday, I received a list from an athletic trainer at East Carolina University, and she sent me a list of 150 or so football and college football and NFL games that were suspended, canceled, postponed, or delayed by lightning. And so we're going to start looking at what the commonality is between cases in terms of what was going on. Did they wait too long? Did they suspend the game? Did they even need to? And so on. And so this has never really been quantified, and I think it's about time because there's a lot of attention being paid to the topic. The other thing I should say is that I went to a meeting of an organization which nobody's ever heard of called the IAVM in Norman, Oklahoma a few years ago. That's where the meeting was. International Association of Venue Managers. Now, they are the ones who actually operationally make decisions at venues for events like this. And when presented with the question of what do you do at a race, an auto race, or other things where people are dispersed, they said, we don't know. We don't have an easy answer. The last part of this is that last week there were 71 people injured at some sort of a rock concert in Germany. You probably read about that. The same event exactly 1 year ago, same place in Germany, there were 32 people injured by lightning. So they are really at risk. I saw the pictures of it. People are spread over probably a square mile with absolutely nowhere to go. So this is an increasing issue, and when these kinds of events occur, they start asking questions. And one of the questions is, how far in advance do you make the decision to evacuate? In this case, where would you go? Probably the only solution would be to have a lot of buses for people to go into because they're portable and they can be driven right to where the people is. But that involves a lot of decisions, a lot of money, a lot of planning, and that's why this is sort of at an early stage. Now, the fixed stadiums, that's a more manageable situation, which is why we're doing the study to see what the situation is.
Yeah, I mean, it's a real tough situation where a stadium that holds, football stadiums can hold, college especially, 100,000 people in their seats. If you have weather, where do all those people go? Courses aren't that big,
Yeah, it's like golf courses, the same thing, golf tournaments. Their attitude was, we need to think about this, and it's been 5 years since I did that presentation, and I don't think they've solved the problem at all. So.
I know the NCAA has some rough guidelines, and I forget if it's lightning within 7 miles or lightning within 10 miles of the stadium. We've worked with UTEP and emergency managers at UTEP to give them a heads up on how far away the lightning is from when the UTEP has a home football game. But like you said, I think right now a lot of different stadium owners or directors are kind of doing their own thing, and hopefully, and I'm aware of that conference, Ron, that took place in Norman, the large venue conference. They can all get together and kind of work with the scientists and the social scientists to figure out not only a plan on when to take action, but like Paul said, what action to take.
That's a difficult problem. One of the things that they raised was that if people are told to evacuate, let's say they go from this open football stadium into a university building nearby, and they're safe, they're afraid that they won't get back in, that somebody can take their seat. And so it's a lot of planning and a lot of human sociology management, which is really difficult for us, and it is a difficult problem no matter how you look at it.
You know, you mentioned that concert over in Germany. I saw that article as well, and like you, I read it, and I was like, it was unfortunate that the 80 people were injured by this concert. But like you said, as you read down in the article, this same thing happened last year, and to me, you know, if it happens once, it's but if it happens again and you still have a plan a year later, there's some questions need to be asked on that concert, concert director, venue director, about why they didn't have a plan in place, and you know, why would this happen 2 years in a row?
Well, I was there at this meeting about 5 years ago just to divert a little bit, and the people that actually put up these portable stages for any type of event, there had been a new design come up, and you may recall that some people were killed when the stage flew off. There was one in Toronto or somewhere in Canada, and then there was another one somewhere in the U.S. 2 weeks later. And we asked these people who had just started deploying these things, said, how good are these things? And they said, well, they'll last up to 50 miles an hour. Return time of 50 miles an hour in the U.S. and almost anywhere is weeks probably during the summertime. So I don't know if they've redesigned these things or what, but it's a sort of constantly moving target that we always have.
Well, we're kind of getting towards the top of the hour here, and I want to thank everyone for joining us. One last plug: if you do have a question, you can ask it with a hashtag, with a tweet via hashtag Monsoon 2016. I want to dispel some more lightning myths, and one that I came across that I never really thought about, but a lot of times when somebody is struck with lightning, other people will hesitate helping them because they think that somehow their body still has electricity in them. And of course that's not true. The electricity passes right through. Is that right, Ron?
Yeah, it's only lasted a portion of a tenth of a second and it's gone. So that unfortunately has led to probably some deaths. And it's a thought process that's relating to electrical injuries where somebody is in contact with a wire and they won't let go. Well, that's certainly a time when you don't want to touch the person. But lightning came and went so fast that you didn't know what happened hardly.
And usually what the person needs is like immediate CPR, because many times if the lightning it just kind of stops their heart and there's not much other injury, so they actually need CPR, and once they can get the heart started again, they're on their way to recovery.
Right.
So they actually do need you to touch them and give them CPR. And I guess in a large group, if that were ever to happen, you have to do a real quick triage to find out who's in the most serious shape and who does need CPR to immediately administer that to them to kind of make sure that you can get their heart going again, and then you can treat some of the other people who may have been a little further away from the lightning strike. Of course, another common lightning myth is that lightning doesn't strike twice in the same place. I know you can talk about that, so go ahead and dismiss that rumor now.
Well, Ben Franklin quoted that. I ran across that in a book about Franklin a few years ago. He quoted it as being a common phrase, and that was in 1770 or whatever it was. So that phrase had been around. I don't know why it started. I think it's because it rhymes or something. The Empire State Building and tall towers are hit multiple times. We use the National Lightning Detection Network to calibrate. We use tall towers like radio towers and TV towers to calibrate the network, and they're hit 10, 20, 30 times a year. So tall, isolated, pointed objects are hit very often.
Hey, Paul,
talk about
what you got on your screen here.
Yeah, I was just trying to look up, and I know Ron talked about some of these statistics earlier, but this is from our NOAA's lightningsafety.noaa.gov website showing 6 fatalities so far this year and how many have happened over the last 10 years. And I know lightning's our topic today, but I want to give a plug for our Friday topic, which will be heat. Heat is a severely underreported how many deaths happen from that. Just in Maricopa County alone, where Phoenix is, we have an average of 80 heat-related deaths a year. So, I think heat is far and away a deadlier weather phenomena than we give it credit for, more than the lightning or the flash floods we talked about yesterday, or the other topics we'll have coming up. And so I'm really looking forward to Friday because we have this huge heat wave coming too. So.
I know it, and I know we'll get the same thing. But again, this graphic goes back to what we talked about earlier. You can see a few pink splotches in there that represent females that were struck by lightning, but the vast majority are males that are struck by lightning. And Ron kind of hinted at the fact that I think that males kind of have an attitude that it won't happen to me, and at least in the United States, most of the time or many times. Those males are ones outside doing the activities, whether it's farming, whether it's fishing, or things like that.
People are just humans are generally bad at perceiving risk, and especially so.
Yeah, if we can pull back just a little bit, I'd like to plug, I'm on the committee for this team, lightningsafety.noaa.gov. That's the best lightning safety website in the world, hands down. The African group is starting up that parallel to that with African input on numbers and frequencies and so on. But lightningsafety.noaa.gov will address, I think, virtually everything we've talked about today. I put the maps and tables up that I showed today on there also. I need to end with something kind of funny and kind of sad. Talking about myths. I was at the conference in Zambia last year, and a near universal myth in Africa is that lightning strikes people wearing red.
Huh.
Where does that come from? It comes from some anecdotal situation that gets overextended, and this is how a lot of our myths are too, that someone who doesn't really understand what's going on comes up with those. So anyway, it turned out that almost every country at this conference said that.
And it's funny because I think I've heard a similar, not a color thing, but in the U.S. I've heard people say if I've got jewelry on, if I'm listening to my iPod or something like that, I'm much more likely to be struck by lightning.
Yeah, we're very much strongly trying to get rid of those ideas.
My wife's chatting with me right now online, and she's up in Wisconsin, and she said it's thundering outside. And then she asked me if she could take a shower. So.
Tell her no.
I told her if she likes I told her if she likes electricity, go for it.
Yeah, well, explain, Paul, why that's not a good idea. Why don't you want to be on a corded phone? Why don't you want to be touching any fixtures in the house during a thunderstorm?
Yeah, you don't want to be part of your house's electrical or metal system that's going to conduct that. So, I don't know. Probably a lot of people don't need to worry anymore about having corded phones. Cordless phones were in vogue 20 years ago. Now everyone has cell phones. So, still taking a shower, cleaning your tub, any of that kind of stuff. I don't know why you would be doing any kind of electrical or plumbing work, things like that. But just sit on your couch and watch TV and take it easy.
Very true. Well, again, it's almost the top of the hour. I want to thank Ron and Paul for joining us today. Again, real quickly, let's go over the highlights. Ron, what is the website that NOAA has that people can use to gather great lightning safety information?
That's lightningsafety.noaa.gov.
And I was poking around it myself today and in the past, and it has lots of great charts, lots of great information on lightning deaths, breaking it down by activities and things like that, but also great safety information. There's stuff there for teachers and for students and things like that. So it's a great source. And again, remember, we talked about at the beginning, there's no safe place outside. We're getting away from crouching down. We're getting, don't lay down. Just when you hear thunder roars, go indoors. It's a safe place to either be inside a safe and secure building or to be in a car that's completely metal, not a convertible, but a car that's completely metal. So, Ron, real quickly, what's the picture there you got up?
Oh, this is one I took from my house here in Oro Valley in Tucson. This is two cloud-to-ground flashes, and if you move the camera back and forth and you use up a lot of time doing this, eventually you'll get one of these. And each cloud-to-ground flash actually has several return strokes. And so the one in the middle, you can see it's bright on the right and then dimmer. So those are, looks like 3 return strokes. When you see lightning flickering when you're looking at it, those are first the return stroke comes down the channel, then it goes, the light goes back up, then the second one comes down if it needs to lower more charge, and then the third one, sometimes 4, 5, 6 of them. So I happen to catch several of them in this picture.
Very good. Great capture, great picture. Well, that's going to wrap up tonight's discussion for Monsoon Awareness Week 2016 on lightning. Join us at the same time tomorrow as we'll be talking about downbursts and the threat that those are in and around the Southwest as we continue on with Monsoon Awareness Week 2016. Thanks for joining us, everyone.
All right, thank you.
Take care.